Welcome to Quantum Neural Networks, one of the most exciting frontliners in artificial intelligence. In this video, we will explore how qubits, superposition, and entanglement are helping to create a new generation of neural networks that could solve problems behind the reach of the today's computers. Everything in classical computing starts with a bit. A bit can be only a 0 or a 1. But in quantum computing, we use something called a qubit. A qubit can exist as 0, 1, or a combination of both at the same time. This ability dramatically increases the amount of information that can be represented and processed. In fact, as the number of qubits grows, computational power scales exponentially. One of the most powerful concepts in quantum computing is superposition. Think of a spinning coin. While it's spinning, it's not strictly heads or tails. It's effectively both. A qubit behaves in a similar way. Instead of evaluating one possibility at a time, quantum systems can represent many possibilities simultaneously. This creates a form of quantum parallelism that gives quantum neural networks their unique computational advantages. Next comes entanglement. A phenomena is so strange that Einstein famously called it as spooky action at a distance. When two qubits became entangled, their states became deeply connected. Changing or measuring one instantly affects the other, regardless of the distance between them of the two qubits. This allows quantum neural networks to model high complex relationships using for far parameters than classical systems. Just like classical computers use logical gates, quantum computers use quantum gates. These gates manipulate qubit states and control how information evolve through quantum circuit. Some gates create superposition, other gates generate entanglement, and primeable rotation gates act like a weights inside the traditional neural network. Together, they form the building blocks of quantum neural network. From earlier slides, we have seen qubits, superposition, and entanglement. Now, let's see how quantum neural network is structured. First, classical input data is encoded into quantum states. The information then passes through multiple variation layers containing trainable quantum gates. Then, after this, gates adjust their parameters during the training, similar to how the weights are updated in deep learning. We all know that thing. Finally, the quantum state is measured to produce predictions or classifications. Now comes the most important part, training the quantum neural network. Just like traditional neural network learns by adjusting weights, but quantum neural networks learns by adjusting quantum gate parameters. Earlier slides, we have seen how the quantum gates works. Training a quantum neural network works differently from standard back propagation. For example, instead of calculating gradients directly, quantum systems use a technique called parameter shift rule. The circuit is executed multiple times with slightly adjusted parameters. On the right, you can see the lost landscape visual, representation of how the model searches for the better solution during the training. These measurements provide the exact gradient information that can be used by optimizers like ADAM, SGD. However, the researchers still face challenges such as plateaus where the gradients became extremely small and learning became slowed down. Let's recap. Quantum neural networks combine qubits, superposition, and entanglement and trainable quantum circuits to create a completely new approach to machine learning. While the technology is still evolving, its potential impact on science, medical, finance, and AI is enormous. We are on the beginning of the quantum revolution, and the breakthroughs of the next decade may fundamentally change how the intelligent systems are built. The quantum era has officially begun. So, if you enjoyed this deep dive into neural networks, quantum neural networks, make sure to like the video and subscribe the channel.